Hi, I'm a PhD student at Stanford, advised by Andrew Ng, and I'm going to present this with Tony. This is work led by Anand Avati, as well as folks from the Stanford Medical School, Professor Nigam Shah and Ken Jung. Okay, so the overarching impact of the paper we'll be talking about today is centered around the question, how can we improve access to end-of-life care to terminally ill patients? And so right now we have a problem in the hospital. Over 60% of all deaths in the US occur in the hospital. Meanwhile, most people prefer to pass away at home next to their loved ones. And determining who should go home due to their condition is usually the job of palliative care teams in the hospital who are in charge of dispatching patients once it's the right time. But they don't know who to reach out to. There are so many patients to chart review. It's infeasible to review all of those patients, but it is feasible to review a small subset, and right now that is a randomly selected small subset. So instead, we present a short list of patients who are most likely to have those palliative needs using machine learning. And so we can frame this as a problem of predicting a patient's survival probability from their electronic health record, or EHR. And the EHR is a record of their hospital admissions, including information like lab tests, their age, and demographics. So essentially what we're feeding in the EHR data, and we're predicting the time to a patient's mortality. And we look across two different data sets. One is one private to Stanford Hospital with about 3 million patients across nearly 30 years, and the other one is a public data set called MIMIC3. And so the lens through which we are looking at this problem is a time to event prediction, where the event is mortality and the time to event is essentially someone's survival. This problem is difficult because we have partial labels on people who are still alive or who do not have a recorded date of death. So we have to apply either right censoring, using their last record of existence, or interval censoring, where we encode some prior knowledge, such as the max age a person can live until, for example, 120 years. And we care about the order of magnitude. That's more important than the exact date at which someone has passed away. So we look at the log scale. And the time to mortality is also positive because we're predicting a future event. And so we use a model to predict, we use a model to predict, I'm missing slides. Why are we missing slides?
I think it might be the next one, actually.
Oh, okay.
Keep going.
Oh yeah, this is, okay, sorry about that. So we're using a model to predict a distribution of someone's survival, so the probability at which that they might pass away across time, as opposed to a point estimate of exactly when they might pass away. And the paradigm under which we're operating is maximizing the sharpness of this distribution subject to calibration. And this has been successfully applied in probabilistic forecasting, as well as commonly used in meteorology. And one such objective that's commonly used is called CRPS, or the Continuous Rank Probability Score. And minimizing CRPS yields sharper, better calibrated probabilistic forecasts than maximizing the likelihood. And it's widely studied and noted that MLE makes models more conservative, sometimes producing higher variance prediction, analogous to M projection, and thus can go against the principle of maximizing sharpness. So we use CRPS as a robust alternative to MLE, and Tony will speak more about how we incorporate that.
Cool. Thanks, Sharon. You guys hear me? Cool. Yeah, so as Sharon mentioned, part of our technical contribution in this work is to introduce a continuous rank probability score for survival analysis. And just to give you guys an overview of what's going to happen, the high-level architecture looks like the following. So we have an electronic health record with which we're interacting at the bottom. Thank you. And at each time step, we run the patient's age, gender, and their diagnosis codes through a recurrent neural network, and we predict the parameters, so the mean and the variance of a log normal distribution. And the entire system is trained end-to-end with backprop. The question that we address here is how to set the scoring rule at the top. Okay, so for the uncensored observations, which corresponds to dead patients in the EHR, we maximize the likelihood, or we know their time of, because we know their time of death. For the censored cases, for patients who are still alive, we maximize the tail mass. And so this is typically what's done for MLE. And one more case that we consider is interval censoring. So in the real world, it's typically known that people typically don't live past 120 years. And so we actually frame this problem as an interval censoring problem where we try to maximize the mass in between these two. So instead of MLE, we use the CRPS, and as Sharon mentioned, in certain cases it's known to yield sharper prediction distributions subject to calibration. In particular, both the MLE and CRPS and all proper scoring rules will give you the correct model under proper model specification. But in the case where the model is misspecified, if your model has heavier tails, or sorry, if the ground truth has heavier tails than your model assumes, then the CRPS is known to yield sharper distributions. So the original CRPS score that has been introduced in meteorology is shown in the first line. We'll give some intuition for it on the next slide. And we introduced these right-censored and interval-censored variants of this score. So the intuition behind this integral, and for succinctness, we'll just show the interval-censored version at the top here, is in the case of the known depth, you would try to minimize the CDF occurring before and after the known time of event. So this corresponds to our uncensored case. If there is no known depth, then we introduce this score that just minimizes the CDF before the time of event. And in the interval case, we try to minimize before the time of up until the time that we know you are alive, and the time after 120 years of age. So this is the interval-centered case. So for results, here we're looking at what the assigned mass is to the what we call unreasonable observations of living past 120 years. So again, this is motivated by a hypothesis that if you use the CRPS instead of MLE, you'll be able to yield sharper prediction distributions in the case of heavy censoring, which is often the case in the EHR data. And so we train these neural networks with the interval and right-censored variants, and in general show that the interval-censored variant with CRPS yields the sharpest distributions. And the calibration curves, unfortunately, are not here, but all these models are more or less well calibrated. And so this is being used to track how well patients progress through the electronic health records. And so this is an example of what we're using with these predictions. So each time step here on the x-axis is an interaction number for a particular patient. And we show the upper and lower 95% confidence intervals that our model predicts for their time to death. And this is for patients for which we actually know their time of death. And so we see that it's not doing a perfect job, but in general, it's doing a reasonable enough job for us to use with the hospital. And just to show one more, I guess, motivating figure is how well we do when we evaluate as binary classification. And so part of the motivation for framing this as a survival problem is to be able to account for the most recent observations in the data set. So if you have a patient who came in, or if you're truly interested in 1 year outcomes of mortality and you have patients who came in the last 9 months, then you can't really use that as a positive or a negative label. And so in the end, what our palliative care team is interested in is these 1 year mortality, the labels. And so this is just to show that we still have decent performance when treating the problem as a binary classification problem. And that's it. Thanks for your attention. Happy to answer any questions.